coming out to our Database Month event tonight. We have with us a really exceptional speaker. This is Doron Levari. He was the CEO of Scalebase. Among other of his achievements, he's got 15 years of IT leadership experience. In that time, he's earned quite a lot of certifications and other achievements, awards. He led training for the Israeli Defense Forces. This guy is an outstanding database genius. Please welcome Doron Levari.
Please continue. And so thank you very much for coming and listening to me today. Basically, we'll talk about MySQL scaling techniques, and I'll also talk about Scalebase. So I did found this company, and we are very excited about what we're doing. We're based out of Boston, and we came all the way here to basically all around the US, spreading the world around and getting our first customers, and feedbacks are great. But usually most of the time I'll spend on standard scaling techniques of MySQL database. Okay, we are all about your database transparently scale. You can keep your database, your MySQL, no new SQL, no new magic, new boxes or things like this. Standard good old MySQL database, but with all kinds of techniques and best practices that can allow us eventually to scale. So I'm familiar with this. Don't see anything yet, but this is a very, very familiar slide by Amazon. It's not mine. Amazon uses it, but it's very, very good to show the scalability thing or the elasticity in the current world. So this is the predicted demand. If I run a business, successful business, if things good happen, if good things happen to me, then my demand will continue going up. Usually I buy hardware, in advance, I buy good servers to keep the demand going, and then plan to buy more hardware when the demand comes up. But even better things happen to my business, and the actual demand is like this. So here I lost, I spent too much money in advance, and I'm not using all my hardware. This is much worse. I just lost customers and lost opportunities because my hardware is not enough. And eventually, what I really want to achieve is something like this. And this is what scalability and elasticity is all about. I can go up and down, and again, Amazon made this slide, show how good and elastic the cloud is. Right? EC2 is elastic computing cloud. I think that when it comes to databases, elasticity is a bit, MySQL databases or relational databases as a whole, elasticity is a bit thing hard to achieve. So what options do I have when I come to really scaling the database and make the database eventually support more users and more data in it? So I can scale up or scale out. Just quick survey, scalability issues. I saw earlier a couple of hands coming up. Which one of you are considering scale up or scale out? Hey, hi there.
I didn't realize there's a difference. What's the difference?
Okay, so let's go right to it. So scale up is basically taking my machine, my database machine, and make it bigger, make it stronger. Put more memory in it, put more CPU in it. Okay? If I have usually I have one database machine, then I can fairly easily can make it stronger and make my database run faster. It's very easy, it's transparent to the application. I don't have to change one line of code, and the database will eventually run faster. But the downside is that it requires some downtime. Okay, I have to shut down the machine. Even if I'm in the cloud, in Amazon cloud, I have to migrate between machine types. requires some downtime, it's very pricey. Okay, Amazon, the largest machine, is a quadruple extra large machine, which costs $2.6 an hour, which sums up to enormous amount of money. And eventually it's limited, okay, because when you go to Amazon, how many are you in an Amazon cloud or any other public cloud, Rackspace, Joyent? Good. So, the cloud is all about virtual environment. It's all about the small machine is tiny. The medium and large and extra large machine are eventually small. You cannot go into the really big, large machine. I don't know, the machines that I had the privilege to work with, all the HP Superdome, all the others with 168 CPUs. Oracle can use those kind of machines. You cannot, even the quadruple extra large, eventually it's limited. And there is nothing more, there's nothing stronger than that in the Amazon environment. So, and more than that, databases, relational databases I call it complex beasts, because especially in writing, when you write a database, you make one update. This update eventually translates to 4 recursive operations in the database. The update should go to the table, should go to the indexes, or index, let's say 1 index or 2 indexes on the table. They also should need to be updated. Rollback segment, familiar with rollback segment, with the term? It's all about isolation. Okay, when I'm a user, if I update a certain value in the database, other users, other sessions are now querying the same database, the same data from the table. They shouldn't see my update. Okay, so they get an older version of the same row from the rollback segment. The rollback segment also used for rollback. If I do rollback, then the older version of this row takes over the new one. Transaction load, a lot of I/O all the time, because database eventually has to write to disks. Nothing you can do about it. If you want data to be persistent, to be durable, you have to write to disk on the commit. Transaction isolation, row level locking. One update command can cause, 30,000 rows to be updated. Every row must be locked before it's updated. And then these 30,000 locks need to remain kept in the memory, in the database engine memory, all the way to the commit, and then they are released. Now multiply all these things with terabytes of data and 100,000 concurrent users. It's a very, very difficult. Eventually the database itself become the bottleneck here. So I can put more CPUs and put more memory in it, but database will not run faster. I'll see that Percona did some surveys, some tests. You see, at the beginning it's okay, more cores bring more performance, but eventually it goes down, and more hardware, more juice you put into the machine, you won't get too much performance out of it. So this is basically
performance per something?
Yeah, this is all performance per core. This is number of cores. There are some models and some actual measures. Eventually, this is throughput. Okay, there's a difference between throughput and performance, by the way. Performance is time. How much time did the query take? 1 second, 1 millisecond. Throughput is how many transactions per second. How many total transactions the database was able to process in 1 second. So it's a bit different measurement, but the more it exhausts really fast, especially with MySQL. Especially with my MySQL database, the more cores and the more CPU power you put in the machine, performance eventually will go down. Okay, MySQL databases where if too much memory, too much buffers for the MySQL memory, it has to clear these buffers and make sure that everything is okay there. And it results in not better performance, but even worse. And again, writes. Okay, database, you can, the applications that are read mostly, or the applications that are read-write. You know, in the old days, usually the ratio of 1 to 9. Okay, one for every update or insert, there were 9 queries, or the ratio between writes and reads was 1 to 9. Today, as you see with the Web 2.0 and the two-way street, there are a lot of updates. There are a lot of within, especially in social networks, social gaming, SaaS applications. You see a lot of the ratio becomes sometimes even 50-50, or even more writes than reads. You write a lot, and then eventually you do some one read analytics, very sophisticated query to pull out all the data. Machine generated data. One of our customers is manufacturing solar panels. Okay, pretty green, but you would expect that every solar panel has a SIM card and a cellular data, and it's keep reporting how much sun, and how much electricity, all this kind of data they must keep in the enormous database. Now they are SaaS providers, so they have tens of millions of solar panels all over the world. All of them report to the same location, somewhere in Europe, and this database is enormous. So, you know, it has to put up with the reporting every 5 minutes of tens of millions of panels, and eventually do some analysis on this data to come up with, we have a tree growing in front of our panels, or a bird did something, bad things with our panels, and so on, in order to replace them properly. This is the aim of this company. So, and it's getting worse and worse in this in this ratio and the scaling requirements. So, we talked about the difference between scale up and scale out. Scale up is basically remaining with one machine, but make it stronger and more powerful. The other solution is scale out. Break the one machine barrier. Having instead of one database machine, having several database machines doing the same work. And it's very common in web servers, application servers. Okay, even having sort of one application server, they have 10 of them behind the load balancer doing the same work for us. Split or balance the users, balance the load, balance the traffic, the processing across several servers. As long as we keep some important rules about the state and talk about it, but it's really possible in a quite easy manner. So I'm not sure what's going on by itself, but the problem is with databases. Databases are stateful machines. You know, everybody knows that when I write my application, I write a stateful application, and then I have to run to handle the state. Whenever the state is updated, I have to replicate it to other machines. Whenever there is an update to the state, I have to handle it, manage it. And the same thing goes with updates to databases. Okay, since databases hold a lot of data, it's very hard for me, and it requires some logic to, and I want the data to be spread across several machines. It requires some logic to handle this kind of the data and the state. So this is my starting point. Starting point for the slide will go by itself. But this is my starting point. I have a lot of users. It's good. I love my users, right? I love my. Basically, what I always say is that the real assets of an organization, of a business, of any business, it can be Facebook. By the way, who are the customer of Facebook? Are we the customers?
Ad purchasers.
Yeah, we're the merchandise, remember that. But anyway, but we are the content. Okay, we are the users. The more content, the more data Facebook keeps about us, about what we like, what we don't like, what our status, and so on. It can bring more value to its real customer, which is the advertisers and so on. So users are great. My business loves the users. This is the reason I keep growing with the business. It's okay. So, and the other real asset is the database, because data is an asset. Is something that grows in time. It's always added. It's never deleted. I shouldn't delete any data because 10 years from now I will want to see and to analyze differences and trends and all kinds of things. And application change. In my old days I was very much into the J2EE and JEE and JBoss versus WebLogic versus all the other things. Today everybody talks Ruby and what was there? PHP.
Node.js.
No, what is it?
Node.js.
Node.js is like NoSQL, right? Node.js. It's
JavaScript.
Yeah. Okay. Cool. I'm kidding. I try to stay tuned, but it's very, very hard. And .NET and so on. Applications always change and rewritten, but the database schema, databases, Oracle is being used for 30 years. And the organizations you see Oracle 6, Oracle 7 and 8 still being used because no one wants to touch it. And of course, DBA, I hope it's still true. These days, DBA make the most money in companies, right? The salaries are highest. But because they're maintaining the data, they're backing it up, they're making sure that everything never fall down and always available. And the database again is one. Okay, this is where we start with, and this is our starting point. We scale up as much as we could. Eventually, we end up with one database machine, several application servers. And what can we do next? So the basic thing, one basic solution is a shared disk, shared storage cluster. Okay, the Oracle Real Application Cluster is something like this. IBM DB2 Pure Scale, which is a new product, something like this. A shared storage, and several database machines are accessing this same storage. There are some solutions for MySQL as well. There are some storage engines that were developed for MySQL that implement this kind of architecture, this kind of access. Theoretically, we scaled out, right? We have several databases, several machines, and they can cope up with decreasing transactions and users and data.
So you have a number of machines that are a number of just machines
Yeah.
from one database store.
Number of machines. Each machine has CPU, memory, and it's all connected to a shared storage, usually SAN, a storage area network, with fast disks that the database is still one, okay? But the processing power can be scaled out, right? I can have several machines manage and distribute the power of the processing between them.
They're sharing one database?
Yeah, they're sharing eventually the same disk, right? The same.
Yeah, but it's the same database.
Yeah, the same database. Okay, so yeah, you got it already, I think, because no, it's still the same database. Okay, if I have 10 terabytes of data, this is the 10 terabytes of data. Some of them have cache and other data in cache. By the way, it's resulting in more products because I have to synchronize the cache all the time. If a row was updated in this machine, it must be synchronized with all the other machines. So it yells in the network, hey, I'm the owner, I log this row, and all other machines, yeah, I got you. They keep track on all the logs, the global logs and global latches and all the isolation thing. Also, going on distributed between all of those machines. Eventually, this becomes bottleneck because the data is growing. It is also a single point of failure. Again, this can be RAID 5, RAID 10, RAID all kind of types, but eventually it's also some kind of bottleneck and also a single point of failure. And the noise, the network noise between them, they are not shell nothing machines, they are shell everything machines. There are 4 machines that are so-called we scaled out, but we still ended up with one database, and it's also very limited. You add more machines, you cannot add with real application cluster. Again, reads are better because you don't have to lock the database. You don't have to lock and do all the magic with the synchronize the cache and so on. But it's still very hard to maintain, very hard to manage, and it's very limited. 4 or 5 machines are the top you can get with this architecture. Some other architecture is this: read-write splitting. You have one database to be the primary, several databases as slaves. Who interview are using this kind of architecture? Yeah, it's pretty common, pretty easy. MySQL application is very easy to configure, to start with. It's a bit later on, a bit tricky to manage and maintain, but it's okay. It's a mechanism that works pretty well. We have one primary, several slaves. The data is propagated as a whole, as a complete copy to the other databases. Okay, the writes can go only to the primaries. Reads can be distributed across several databases. This is scale out. Okay, because I have several machines, I can scale out the reads. I still have a problem with the writes. So the bottleneck is still there with the writes in the primary database. And I still have a problem even with the reads. Why is that? Because A, they are eventually consistent. Again, it's okay these days to be eventually consistent. But with reads, if I made an update, I won't be able to read it. During the same transaction, I won't be able to read it from the other machines. Why is that? Because I didn't commit. If I didn't commit, the log was not propagated yet, and it's never going to be in the other database. It must be in the primary database. And also, and it will take some time for the reads for the data to be propagated from the primary machine to the read slaves. So this is. We have to bear that in mind, although it's sometimes it's okay for some applications. Another problem, which is a big problem, if I had 10 terabytes of data, this database is 10 terabytes, this one is 10 terabytes, this one is 10 terabytes. Let's say, it's a lot of space, it's a lot of, it costs money, but it also doesn't really help me with accelerating my reads. Because read is still big data, slow read, slow performance. The database need to work very hard in order to complete my query and do my joins and all the other things with this kind of application. Okay, so and again, the writes are still bottleneck. Multi-master application. Who does this kind of architecture? How do you do it? With 3 databases?
2.
With 2.
2 databases, each database with 2 slaves.
With 2 read slaves. Nice. Nice the presentation. It goes like this. Usually, multi-master application with 3 databases is not really it's not really possible with MySQL, but I have a lot. In Oracle, for this matter, this kind of architecture is supported for 10 years or so. Oracle have several ways to perform this kind of thing, and there are a lot of people in the MySQL world talking about, someday we'll have also a multi-master application, several machines that can get reads as well as writes, and can synchronize between them. And, okay. Oracle has several ways to do it. It's Oracle application option, streams, golden gate, another logical step, another architecture of Oracle. What it basically means that I can read from any database. Those are still made complete copies. All three databases, complete copy of the entire data, 10 terabytes, 10 terabytes, 10 terabytes. But I can read and as well as write to any of the databases.
Is this a partition database?
Come again?
Is this a partition database?
Partition?
Or is it the same data as on the same database?
Same data.
So what are you gaining by having the same data on multiple machines?
I can read from every database. I can read the same data because I don't need to know where the data is. I can put a load balancer here. I can use these database or these database. They're all the same. They will answer my query.
Based on what? How close it is to the user or something?
Yeah, you can. They can be geographically, distributed geographically, and they can. No, even in the same data center. Okay, our goal is, I remind you, our goal is to break the one machine boundary. Okay, I want several machines to cope with my 10,000 concurrent connections. I have a lot of concurrent connections. One database will choke.
Okay, so they handle different users each machine.
Exactly.
Yeah.
Exactly. So if my application server has 10,000, they will be distributed equally. They will be served. Reads will be, like it was in the previous configuration, and writes can be all. It won't be choked and won't be bottlenecked on one machine because writes can be splitted or can be distributed on all of those machines. Question?
So with this architecture, you're getting performance at the expense of storage.
Yeah, you can say that because storage again I have to multiply the storage, but I can distribute my users and get more performance. The problem is where I enable write, and let's say not balancing my writes and have all records and all data can be written in all databases. I get conflicts. I will surely get conflicts. What is conflict? Conflict is a situation where, but imagine the two users, and I have thousands of those, right? Two sessions, concurrent sessions, want to write to the same row. In one database, if it was one database, then I would have done row level locking. The database would serve the first user that comes, the other user will stay in line, stay in the queue, and until the first user commits, and then the second one will come in, do the update, and this way the database will maintain consistency of the data. When there are several databases, row level locking is done on the database level, but if a row is updated here, and the same row is updated on the other database, the logs are not synchronized, such as they were in the cluster, in the shared disk cluster. This is the reason why they synchronize log all the time. Here, data is propagated asynchronously, so the row will be updated here and committed, and the same row will be updated here by another user that is on this machine and is committed. And then asynchronously, the data will be propagated between those databases. And what will happen? I will get a conflict. First of all, there is a lot of noise because if there are three databases, I have 6 errors. Every database must push the updates to all other databases in the cluster, in the environment. So if I had 10 machines, I would have had here 90 errors, 90 connections to all other databases, and push the updates that happen to this database. Let's go over the conflict once again. Let's take this very simple, very, just to begin with. This is one row, one column, one table, one value. I have zeros, okay, in this one column, one row, one table on all databases. Now, the user comes and change the 0 to 1 on the other database right here. So it's updated to 1, and then the database pushes the update to the other databases in the cluster. So change the 0 to 1 to the other databases. In the same time, let's say in the same millisecond, another session updates the data from 0 to 2 on the different database. And the database asynchronously, once every 5 seconds, once every X time, will push the update to the other databases in the cluster. What did I get here? I get a conflict. Okay, so I get not a conflict, 3 conflicts. Conflicts are always, they never come alone. They always come in groups. And so I have a conflict in the first database because it's the update from 0 to 2 fails because there is 1 on the database. The other update from 0 to 1 fails because there are already 2. The current value is 2. The third database, I'm not sure. It can be 1 or it can be 2, depending on which update came first. And the other update that came second will result in a conflict. And there are 3 conflicts. In Oracle, they have large error tables. And they are always, it starts with 1, and then another one, and on different databases. Now, what I get here? I get different values. Now, if this value is now 2, I want to update it to 4. Now, another update, 2 to 4, will be propagated to all databases. It will fail as well because there are gaps to begin with. Okay? So, this is just a very simple example. By the way, let's imagine one user was updated 0 to 1, another user was updated here from 0 to 1. Okay? The value is the same, but we still have conflicts in the database. We still have DBA work to do on these conflicts. Why it's happening? Because there is no ownership of the data. Whenever I allow my sessions to update the same data on different databases, I will always have conflicts and gaps in the data. Eventually, it will go out of control because just being more and more, and it requires manual labor of understanding, updating all the databases accordingly. Now, again, what I've seen in the past is this, and another issue is who is dealing with this conflict? The DBA most of the time. But the DBA doesn't know what is the correct values. Is it 0 or 1 or 2? We need someone who knows what the data should mean. The DBA hardly ever know what the data is all about. It's just numbers.
Excuse me, each of these updates has a timestamp, right?
A timestamp might be a conflict resolution. First of all, no. So update doesn't necessarily has a timestamp. For the database itself, I go back a bit. The database gets an update and then gets the update from the other databases. It's at other transactions. It's in the chain of transactions. Those databases can be on different time zones. The databases can be on different timestamps, and they're not synchronized in the clocks. You can say that there is all theory about conflict resolution. There are some automatic conflict resolution algorithms that Oracle, for this matter, again, this situation is not yet in MySQL. In MySQL, you have multi-master application with one database active at a time and only with 2 databases. So you can have two databases with multi-master replication, but you can't have conflict because one database is updated. It gets all the updates. It's more like the different, like the previous version we had. So for database, you can use if you have the timestamp in another column, then you can use it to resolve the conflict. Again, I won't go into it not right now, but even timestamp is not a good way to resolve all kinds of conflicts, because this third machine, for example, it depends which row came first. You can't control the way that updates are propagated across this cluster. It's all very, the asynchronous thing here. If it was synchronous, then you can control the time and the sequence of the transaction.
You have a race condition as well.
Yeah, exactly. Race conditions are all over the place, and remember I told you that those updates occur in the same millisecond, but they don't have to occur in the same millisecond. They can be, in the same window of the replication of the push, of the update push, and so they will resolve the conflict. The push of the updates can happen, I don't know, every 5 seconds, every 10 seconds. In 10 seconds, a lot of things can happen in the database. You don't have to be exactly the same millisecond to have a conflict. It can be all over the place, really quick. What we solve is just update conflicts and one type of an update conflict. There are more types, and there are insert conflicts. What if I inserted two rows with the same ID? Okay, I inserted ID X to database A and ID X to database B, and then delete conflicts. These are the worst. Okay, I deleted a row and deleted the same row on another database. Okay, now I have a conflict because the row is not there to delete. Now it's not there. I deleted it. It's okay. The data is okay, but still I have errors in my database, and my DBA has to be very busy. Automatic solution is very limited. For the conflict resolution, again, Oracle database, a lot of mechanisms around here, but it doesn't help. It doesn't help about with two nodes. Some are deterministically good, but most of them are simply don't work. A lot of manual labor, and whenever there is a data diff, different data in databases, the conflicts keep coming. The only solution, if you have such configuration of multi-master application, is have data ownership. Have one place to update the data. Either the entire database is the primary and other are slaves, okay? Or we partition the data in some way that, part of the data is updated in database A, another part of that is updated in database B, and so on. In this case, conflicts are avoided. You have to design design an application accordingly. This is the only way. All other things are mechanism. Okay, the mechanism is there, but it won't work for us unless we put major design considerations into it. So let's take, we'll go into the ownership later on, but let's take a step back and talk about partitioning. So partitioning is very, very good. You asked about partitioning earlier. What is partitioning? I make the starting point. Starting point, I have one database, one big database, but I use partitioning, which is a way to order the rows together. Okay, according to some key, branch, list, or hash-based partitioning. I can have, instead of having one giant table that is very, very heavy to read and write, I have the same table, but split it into several files inside the same database, and the numbers, are amazing. Some research that was done, I think, MySQL 5.1, 5.5. Look at the numbers. Okay, with InnoDB, from reading reading from table that took a query that took five minutes. It ended in 13 seconds. Okay, in MySQL, the improvement wasn't so big because MySQL is faster anyway. But the fact that instead of accessing a very large table, I need to access a smaller portion of the table because the table is already partitioned. The database can know, it doesn't have to go to the entire file and scan it from the beginning to the end. If the table is splitted, it's partitioned into several smaller files, and some of those files are needed to complete the query, then it will take a lot faster. This is a good idea. Still, although it may result, it does result a major performance improvement, writes are still problematic. Why? Because every write still have to go to the logging, and to the transaction, the isolation, all the segments, and everything is inside the same database. Although the table is partitioned eventually has different files within the same database. So all the database mechanisms remain the bottleneck. What is the next solution? Sharding. Basically, sharding is taking the partition one step forward. Instead of having partitions of the table within the same database, I have one big table. I partition it into separate files within the same engine, within the same instance. I take these files and put them on different databases. I split according to range, list, or hash. I put part of the data here, part of the data here, part of the data on this database. All of those MySQL databases, all of those standard MySQL databases, but they hold portions of the data. If I have 10 terabytes of data, I have 3.3 here, 3.3 here, and 3.4 here. Okay, so the data is split across the different databases. The users, okay, the sessions are also split across those databases. You know, Facebook, I mentioned them earlier. They are using this technique. On how many databases? You know, 30,000. Okay, because they have 1 billion users to manage. So they have records. Okay, they split the records of those 1 billion users, and out of those 1 billion users, I'm not so active in Facebook, I must tell you, but I'm not a case, right? I'm not a representative case. There are hundreds of millions or tens of millions of users that are active, clicking at this moment on statuses and doing their friends and relations and statuses and all these kind of things. If my profile is here and my wife's profile is here, then if both of us are clicking on the same time, this database will take some of the load, and this database will take some of the load. They won't interfere each other because the data is split across those databases. They won't have, no, the data is not duplicated. I don't have to log because the data appears only once. My profile is only here. There is no chance that my profile will be updated here and here. And then it will be propagated and so on.
What do you mean by profile?
Profile, my record, or let's say my data inside my Facebook profile. Okay, my data that's related to me that is saved in Facebook database or any other. No, it's just an example of taking the data, the complete data, and split it across several databases.
But that will have the issues with the analytic functions, right?
With
Analytic functions.
analytic functions, such as
I want to see the top rank.
Yeah, I agree. First of all, again, while this method is very easy and you know, this is really scale out. This is really taking the one big problem, the one big database, and cut it to several smaller databases, put them away from each other. They don't have to speak between themselves, but the application must be aware. Or the classic sharding, it was implemented by the application itself. I should know that which rows and which portion of the data is here, which portion of the data is here, in order to access the right database. And true, if I want some query, how many profiles do I have? Select count star from Facebook profiles, enter. Okay? I have to, in Facebook, I have to run it 40,000 times on 40,000 servers. Okay, and then accumulate the results, and then after I do that, it's not relevant anymore because another 1,000 users will join. So, no, but this is life. However, if I did have written some mechanism, let's say, that runs this count star in parallel, and select count star on all databases. Every database will give me the the amount of data on every instance. I get 30, 40, 20, and then I'll be able to accumulate the results. It will run in this case. It runs 3 times faster because something like this, even more, because getting a count or getting some mean, max, every analytic function, every analytic function out of a very large table will result going and counting all the rows. And if it can be done in parallel for several instances, every count will be very small and efficient. Then summing them up is very, very easy. So it's much like MapReduce, much like what Hadoop is doing in its own turf. Splitting the big problem to a lot of small problems which are very easy to solve, and then just aggregating the result. But again, this is very, very hard to implement by oneself. Yeah.
Do these databases know about each other? Does the third database know it's only a third partition? There's other partitions out there. Or are you actually creating new individual databases and then you programming on an application level? This is the first partition, this is the second partition.
The latter, the second. What you've been asking, it's a good question because this database doesn't know it's part of a game. It doesn't know it's part of the entire environment. It holds data. The data is consistent, by the way, because it holds data that is, in his view, it's 100% of the data that it holds. It doesn't know that other data is stored in other databases. He is the only source for this data. There is no updates. There are no errors. You see that? There is no propagation of data. There is no pushing the updates. Nothing. The data is on this on database A, B, or C. Who puts the data? The application. The application must be aware of. Outside the database, I should know which data is where and how to access it and how to if I have to update profile X or row X, if it's on A, B, or C, and go to the correct database and update this row. So this is basically the idea of sharding, which is it's not a new term. It's been there around. It's implemented by all NoSQL or most of NoSQL databases. In relational database, it's very hard to implement. It's implemented by some application, in the application level. It's very hard. It's very easy to start with, but it's become very, very complicated in time. Because how should I partition my data? According to release, hash, range, which key? Profile ID or date, whatever. Some tables are split. Okay, some tables are partitioned or split across several databases. Some should be fully copied across all databases. Okay, if I split my profiles, my users table, okay, think about all the satellite tables, the tables that I use only for joins, for foreign keys, the joins. The states, the table with 50 rows, not more than 50, right? Then that I have users from all states in database A, database B, database C. So if I want to join, I need them locally. So those tables need to be replicated. If another state comes along, I have to add it to all databases and make sure it's really added and it's maintained this way. The same goes with updates and so on. Aggregate query, okay, for query data from multiple shards. I want to select the count star, okay, or select star, order by X. I have to get a result, which is a result of queries on all databases, which is ordered, okay, in one result that we ordered from the beginning to the end. Again, order by, group by, counts, all the aggregate functions, rebalancing the data. I have 3 databases. Things are going well for me. I need another database. I need to go from 3 to 6. To add 1, maybe 3 to 4. How do I redistribute the data? Maintaining esteemed, transactional consistency, I have to two-phase commit or do something that will allow me to maintain the esteemed atomicity, consistency, isolation, and durability. All the things, the good things that transactions give me in databases. So, another challenge and administration, monitoring. I had 1 database, now I have 5. Again, they're working together as one, but still I need to backup, restore, manage. This one is not going so well. Why? This is some other. Why don't ever write your own sharding code? Visit outside. But
Facebook did it. Facebook did it.
Yeah, Facebook did it, but Facebook has a team of 20 people. And that all they are doing, again, Facebook, you know what, it's okay. Facebook can do it by themselves. I think that if I don't recommend any one of you considering or want, again, it's a good thing, it's a great thing, it's what I wanted to show you at the beginning of the start speaking, is that there are all kinds of ways, and you can go multi-master, you can go window splitting, and go share disk clustering, and all. Every solution has some, can scale reads, scaling writes is a problem. Scaling writes is an issue. Sharding is maybe the only way, and I'm DBA for a long time. How do you scale an insert? You have insert, you don't have one, you have the solar panels, right? You have, I don't know, 1 million inserts per second. How do you improve them? DBA sometimes, always. We come to a query takes 30 minutes. And then we do some magic, create an index, reorganize the table, and boom, it's 30 seconds. I put a serious face and get something money and go to the next, and I go to the next happy customer. It's not the case with insert. With insert, the data should be inserted to the table and go to the disk. How can I improve it? Okay, and while going to the disk, it has to update the indexes, the rollback segments, the log. It has to lock the row because it locks the row on the index, because if another user wants to insert the same unique key, it will be locked, it will wait, so on and so forth. And I have 1 million of those in parallel, at the same time, working on my miserable one database that with one disk or one storage device that need to get all this data. It doesn't work. It doesn't scale. It can't scale. If I work with something like this, okay, then this million inserts per second Facebook is spread. It really spread across all these databases. each database logs itself, but this database doesn't see million itself. It sees only 1,000, which is enough, but it's bearable. It's something that can be managed in one instance, and it's called make real choking probe. So this is probably really the only way to really scale writes and also reads. Why reads are a lot faster, because if I need to scan, if I need to read, this database holds much less data. Only 1/3 of the data. The query will run 3 times faster, at least. Because sometimes the database goes like this with query performance. If the data doubles up, the performance times 10 sometimes. So shorter table, smaller table, shorter query times, more efficient buffers for reads. And for writes, everything is smaller, everything is much more efficient. So basically, it's a good solution. However, it's very, very complicated. And now let me tell you about Scalebase. Okay, if we have listened so far, then what Scalebase is basically doing is giving the good things of sharding and make your one database, one MySQL database, and make it 10 almost without any code change, almost without any other. You have MySQL, you continue having MySQL database, you work with the InnoDB or MyISAM. Be my guest, we have customers with MyISAM that work, now it works even faster and logs a lot better. No code change, no data migration. Okay, you don't have to migrate the data, because data is already there. Scalebase is one-stop shop. Okay, it holds a lot of tools that will allow you to start federating the data around, going from one database to 3 or 4 or 6 or 10, and start moving the data behind when the application is even still running. So this is what is basically all about. Scalebase is, we call it a load balancer, a database load balancer, the first database load balancer. Why? Because we really can have the database, split it across several, in this example, 4 databases. Each one of them holds a portion of the data. They are not copies. And we stand in front of them, and we know where every data resides. We know how the roles are distributed. We get a query from the application server. We look and feel that any MySQL database, the same driver, the same everything, even MySQL dump, MySQL command line, MySQL workbench, all tools will connect to Scalebase and see a database. But in the back, there are 4 different MySQL standard databases. We don't install, we don't do anything with them. But the only thing that we know where every piece of the data is. And we can route commands to the right database. We sometimes execute commands in parallel on all databases, and we have great parallel multi-threading, so and so, to execute the command on all databases, on some databases, on the relevant databases, and aggregate the result. We support order by, group by, aggregate functions, everything that you can imagine. We have some limitations still, but
so it looks like the bottleneck now is Scalebase.
it's a good question. It's a good thing. So I think that what if I told you that Scalebase, this example we don't see it, but Scalebase is a central management. Central management is where you manage the Scalebase and the configuration. You can also see all the databases and so on. But Scalebase load balancers also can be, Scalebase can never be a bottleneck or a single point of failure, because you can have several Scalebase machines that are, in their turn, are also shell nothing. As long as you are shell nothing, as long as we don't keep state. We get a command, we take the command and run it to the database. We are not the database. We are not replacing the database. We're just serving the database better because we split the data. We let the MySQL do all the dirty job and all the hard work that is doing so well.
So would you have a load balancer in front of Scalebase?
Yeah, you can have a DNS load balancer or any Elastic load balancer. For Amazon Elastic load balancer works very well with us. Some TCP load balancer in front of Scalebase can be used very well. It doesn't matter. It's free Scalebase. It doesn't matter. You see them all. You administer them in central management, so you manage them all in one place, and they all share the same configuration. So they act the same. We have some implementation with the Scalebase, which is software. Okay, we are software providers. We don't do hardware, or we do come as a virtual appliance in Amazon, AMI, and we have VMware, but and also in RightScale, soon to be. But our software can be installed on the application server itself. So sometimes, I'm not sure if it's the best idea, but we can run on the application server itself, and application server connect to Scalebase as a database, and all we have to do is change the IP to go to Scalebase as a database, and then go to all the databases we see here. Now, let's say, and I mentioned earlier that even with Sharding or even with master or whatever, we can still have standby databases. So in this configuration, we have 4 databases that the data is split between them, and we have for each database a backup, which is maintained by the application. MySQL application is propagating the complete copy of this portion. Scalebase connects to these databases, make sure they are alive. It can do without splitting for the shard level. Queries will go to standby C or primary C. Updates will go to primary C, and will propagate it later on to standby C. We can also do failover. Okay, when primary C goes down, Scalebase try to make sure heartbeats and all kind of magic to make sure it's really, really down, and then routes all the queries and updates to standby C, which now became primary, and the application doesn't know about it. Okay, this is yet another load balancer kind of mission that the Scalebase is part of our world as a load balancer. The application couldn't tell the difference between one database and things. Yeah.
So I'm trying to look at this and compare it to Sharding.
Mm-hmm. Sure. To answer.
Yeah, you go ahead.
Basically, what we're doing is transparent sharding, we would say. Kurt Monash, dbms2.com, is a great analyst and wrote about it several times. He called us transparent sharding. We give sharding goods without having the programmers to develop the sharding algorithms and to understand the application. Doesn't know when every bit of the data is. It's connect to the database and get the complete results. It sees, even the management here, the management DBA, it can connect to the Scalebase, and it wants to add an index. We want to optimize the table. Optimize table, XYZ. Enter. Scalebase will get this command and do it and distribute it on all databases. Optimize table can take 1 hour or more on one table, one big table in big databases. Here it will take a quarter of the time.
So it's kind of like, sorry.
Yeah.
I was just going to say, so it's kind of like a black box in the sense that you tell Scalebase how many machines it can distribute the data across, but you're not quite sure how it's going to. Are you, do you determine how the data? I mean, you have to be a Scalebase expert to know. Okay, here's how the data is going to get distributed and stuff like that.
So yeah, you can do either way. Basically, you always know and understand the configuration. You control the configuration according to which Scalebase is configured. Scalebase supports like it supported in partitioning, hash-based, branch-based, list-based. I can say, okay, users 1, 2, and 4 are here, 6, 7, and 10 are here, and Scalebase will make things go to the right place. Or you can have hash-based. Hash-based, you say, I have 1 million users, and I won't give you the list of the ranges. You do your magic and have distributed for an endless user distributed across those 4 databases, and that's all. If you drill down a bit inside, so these are the 5 building blocks of Scalebase. There's a Scalebase analyzer, which is a tool that can help us find a way to do the sharding. Most of the times, from my experience, if in social gaming, usually it's the user ID, profile IDs, Facebook profile ID. It's always in our solar panels. It's the field ID. The field is a collection of panels, right? And the customer chose list. It knows which fields are big, which fields are smaller, and it can play with it. And as for capacity planning, Scalebase kind of eliminated the need for capacity planning. Now, it's not that I preach for, that's not the organizer, not do capacity planning, but you can start with 4 databases, then add the 5th databases, and get several data, or the hotspot. Scalebase can do it even for you, and identify these hotspots, and move them to the new database, and redistribute and rebalance everything that needs to be rebalanced. So the analyzer kind of go over the schema, the SQL log, and identify the recommended configuration for the sharding, for the split of the data, which tables are split and which tables are global, are maintained as a whole in all databases. Scalebase does that as well. So if an update, let's say the insert for the state to the state table, Scalebase will do it in parallel on all databases and return OK. So going back to here, so this is the analyzer. The federator is the moving the data across databases. It can be going from 1 to 4 in the initial phase, and going from 4 to 5 in a later stage. It can be, and also it can be done during runtime. While the application is running, because Scalebase is sitting in front, he knows, with every command, he knows if the data now moved to another database, Scalebase will route the command to the correct database. Dispatch and aggregator are the main function of the load balancer itself. Dispatch the command to the right database, aggregate the results if there are more than one database. Reviver is the failure of capabilities.
So for your application, you support the automatic rebalance the data, or it's a have to manually maintenance?
Rebalancing, the initiating of the rebalancing is manual. We don't. Although we have it on our roadmap, having, okay, let's spawn more machines in Amazon. If you are on Amazon, let's say you use 5 machines and we see the data is growing and the number of users is growing, then we are able to have more, to spawn more machines and start distributing the data. We have it somewhere in our roadmap, but right now we do support adding more machines. You have to add the machine. You configure Scalebase here. This is the new machine. Now start rebalance. We start moving the data around. If it's hash-based, then we choose the rows we choose which data from each database to populate the new database. If it's list-based or range-based, like it is with partitions, you say which values and we do the rest. Okay,
what is
so
a list-based thing? What is list-based? How does that work?
List-based?
Yeah.
What is it?
How does it work? Yeah, what is it?
Yeah, it's the user provides a list of values. First of all, the sharding configuration basically which tables and which column, according to which column, according to which key, the data should be split. So let's say a table that
Well, it's discrete as opposed to range, which is.
exactly discrete. Discrete values. We support, let's say, a list of values for each database and a default. You can say default will go, or unlisted values will go to number 5. It's risky, of course, but it depends if you want to have an exception for a non-listed value or on the default, the value that we didn't configure explicitly in Scalebase will go to a default shard. Only is possible. Ranges are very, very common with dates. Okay, for example, right? It's very common to partition by date and also shard by date, although sharding by date maybe because it's bottling, it creates a hotspot on the current. So database 6 with all the current will always be much busier than other, but it's, no, this is why currently we are working with our customers to understand better, and we're improving our product. We are something like a year and a half working on this product. We have a lot to learn, help our customers, help us back. Yeah.
Yeah. Further question is, does your product taking one step further to be able to run parallel query on given node?
On a given node to be parallel?
Yeah.
It's a good question. We can do it.
Which current MySQL does support?
Yeah, we can do it like MySQL doesn't do it so well. Oracle, I know how Oracle is doing it, and the same thing can work on the same node as well. Yeah, it will be. It will be somewhere. Being us in the middle, we can do a lot of things. We can do. We thought about having some. We can do. It's a great place to be because we see all the database behind us. We see all the commands. We can encrypt data. Okay, we can put data and we can decrypt and put database and on the select encrypt. Let's say credit card, social security. We can do all kind of security things. We can do caching. Okay, we can keep some of the data inside Scalebase and bring it right there. We're not doing it yet. It has pros and cons and so on, especially when we add more Scalebase machines to the environment. But yeah, we have plans. This is some benchmark that we ran. Okay, we can see that we started with one database, 2 databases, 4, 6, 8, 10, and 14 databases. Number of connections are growing. Number of total database size. We ended with 84 gigabytes of database. It's not that big, but it's only just to get the sense of the throughput that is keep going and going and going. Okay, when again, if sharding is done correctly and basically sharding can be unlimited, as Facebook and Zynga and Tumblr and Flickr and all the others that implemented it themselves. Eventually were able to scale indefinitely. Because as long as the machines are really share nothing and distribute data and concurrent sessions.
I wouldn't say unlimited because you have to eventually partition your index, right? Where you know where data is. If you have hundreds of thousands of servers, you have to know your index could be slow.
My index? Our index?
Yeah, so your thing that knows what to do is select. That can eventually be slow if you have huge amounts of partition data. For like Google, for instance, right? They had to write pig because they just couldn't get the data out fast enough. They have to
So you say when the data is so big and so partitioned that the metadata itself, our metadata, because we don't keep data. You're right about it. We also checked. I think we are great users of Amazon, by the way. We pay thousands of money, $1,000 every month for the RDS instances that we bring up and down all the time. And we tested it with 500 machines and a lot of data. Yeah, we're improving it. Basically, what I'm saying is that you need to have a lot of data, a lot of servers in order for the metadata itself to be a bottleneck. Because basically we bring all the metadata in our memory. We're not such memory consumers ourselves. We love our CPU and our multi-threading and all the other things, but we're not high memory or high I/O disk at all. We do a lot of networks, but it's hardly ever a bottleneck. We are very efficient in how we identify. Okay, this row, this query needs X, this database 6. We come to a conclusion really fast. Okay? And we also support some kind of optimizations, hints. If you know better than I am, then you can put the hint and then we route according to the hint. A lot of good things going on. How are we with the time? We want to go home? Almost there. Another very interesting thing that, again, I was dumb until I met my customers that make me a lot smarter and help me build the product the way it should be, like the customer. They know best. Some very unique and special architecture that I want to share with you is I call it GeoCluster, which is service can do it very easily and in a very unique way. Consider this configuration, this architecture. I have a lot of users. I can be whatever, Facebook or whatever other game. Let's say a very intensive gaming site that has users all over the world, in Australia, Asia, Europe, and the US. Now everything is, all users, all activity in one MySQL database on a very big machine that reaches long ago. And it causes major problems. So, first thing this customer is doing is split the data. Split the data according to list. It has a column called country or continent or code, whatever, for the user profile. According to the list of it has 4 distinct values. Every value is in a different database. With Scalebase, he was able to split the data across 4 databases. Those are 4 primary databases and 4 backup databases that serve his entire data split across those databases. US gamers are here, Europe are here, Asia, Australia, the gamer and everything beneath it. Okay, the entire cloud or cluster of data, the gamer name, and all the games, the balance, all the activity is split across the database. Okay. Now we came from this architecture to this. He created 4 different sites in Amazon, and having Scalebase in every different site, in the US site, Europe site, Asia, Australia. In every site, the primary database that holds the users of the site. So if you take in the US side, the primary of the US people is in the US, and all other sites have the backups, standbys. The European, the green, is the primary, is in Europe. Okay, they don't have to be like this, all of them the same data center. They can be, but the configuration is the same. Okay, the data is sharded to 4 servers. And each server has another 3 slaves that can be used for reads. There is the DNS load balancing that if I browse from the US, I'll go to this site, to this application server, Scalebase. This application server will go through Scalebase to the database and get all this data. Now, if I'm a US gamer, I log in for my home in the US, if I change something in my profile, it will be updated locally in the US, blue, primary. If I need to read my friends, other friends, other profile gamers, the reads are also locally, local. Now, if I took a plane and landed in Europe and logged into my account, then I have some latency because again, updates are done only in one place. Remember the ownership of the data. If I allow updates of US records here, some batch or something else that will update my record in the US, it means that in the more rare cases, when I'm not at home or I can still walk, but it will be a bit, it's again transparent and everything, but the update will go to here from this Scalebase. Here, and reads will be anyway locally. And in this configuration, 99% of the writes are local, 100% of the reads are local, and it's fully redundant. Because if Australia site went down, completely down, it was a flooding, power outage, then Australians, then Asia took over the primary database for the Australian gamers. When I browse from my home in Australia, the DNS load balancer will put me on the Asia, on the Asian site. I will be able to update the application will updates in the Australian profile will go locally. Reads will anyway go locally, and all other scales all other configuration will be automatically synchronized because even the US will know how to update and read from the new configuration. Everything basically it is the same configuration.
You said writes are 99% local?
Yeah.
What do you mean? Why 99%?
Usually, if I'm in the US, again, the goal here is to distribute the rights, okay, across the world, not to have all the rights go to the US like it is today. Today, the one database is in the US. And the Asian gamers have to go all the way and update all the way to the US service. Now, if I'm a US gamer and I'm in the US, then I browse from my home, I'll be here, and the application doesn't know. If you issue another command, Scalebase will route to the primary, which is in the US. Now, if I go and take a plane to Europe or Asia, in this case, again, the application will run the same, everything. The application didn't have to change one line of code. But automatically, my role, okay, if I browse, the DNS load balancer, which is the main load balancer, will put me on the Asian side, which is good. I get better response time. The application will issue the update, it will go here, and then distribute it by the application across the...
So the write will only happen if you happen to get DNS load balancer and then you want to smear data. You don't know, oh, there needs to be an update to that data, and it'll pull it. I got you.
Exactly. So the update will go to the one primary inside this configuration. Again, this is new. It's really distributing my data, my writes and reads. Reads are always local, and eventually they happen more. And we get fully redundant configuration with real distributed multi-load balance, multiple sites and multiple geographic location, also DLP, and improve performance because they bring the data local to the local location. So let's summarize. We talked about scale up. Scale up is making the machine bigger and bigger and bigger. It works to some extent. Again, SSD, I didn't mention it, SSD drives. So SSD drives are great. Okay, they improve performance. Writes and reads. Eventually, we will come to the limit even there and then. Shared disk cluster. One disk, one storage, several servers is not really scale out. But it has a limitation. Without splitting, multi-master application with all the conflicts. Yeah, don't try it at home in production, but think about all the situation, all the use cases that you might get. It's amazing. Ownership is very important. The data must be updated on one place only, and from there go to the other places of it. Partitioning and Scalebase as a sharding or an enabler of sharding. Sharding, again, is a good solution, but don't do it yourself. Scalebase is an off-the-shelf product that has all the ability and all the tools you will ever need to take your database and make it serverless. Really scale out, be elastic. The database elastic. That it should be. Your cluster is another interesting thing, and that's about it.
Before we move on to the Q&A, I just want to give a big thank you to our fantastic speakers. Doron Levari, CEO of Scalebase, and I want to give a big thank you to our generous sponsors, and especially the Ladders, who's provided us this amazing space. If anyone's seeking a new role, talk to Andrew. He'll help you get it. And Q&A, who's got the first question?
Backend node is each server connected to Scalabase, or is the whole piece Scalabase with the charts?
Again?
I read on the Scalabase site that
It was you then.
the price depends on the backend nodes in part. So, what is a backend node for Scalabase?
If I understood correctly, you can have several database nodes, okay, managed by Scalebase. You can have several Scalebase instances. All of them see the same architecture, same configuration, the same nodes, and you can connect to each one of them and get the same.
No, I think he's asking is a primary and a slave one node, or it's just a primary node and the slave is another node, and you have to pay for both of those. That's what. He's asking what is a node in the Scalebase pricing. Even what does a node make up?
What do you want to do?
Open source.
Then my VC will be angry at me. No, I'm sorry. So, well, we can basically it all depends why configuration is. If the node is only for failover, then it's one thing. If it's used for reads, it's another thing, and eventually it's a fraction of the price. You can say it's not a fully functional node. We have customers, by the way, that not that I encourage it in any, but customers that start with the splitting only. They don't do sharding. They have one database and then full complete replicas. By the way, Amazon RDS with one checkbox I can have read replicas, right? Familiar with it? Now, okay, I can have replicas, which are great, by the way. It's very easy to spawn them, to create them. Amazon make the magic to make them updated all the time. But I have to write my application in a way that it accesses the reads and writes. And if I made an update and then read, I want to read my update, right? I don't want to read. Oh, where's my update? It's not there because I went to the replica. So Scalebase is you can very easily configure Scalebase to manage one and then another. It's very non-expensive.
So what's the
You pay Amazon more.
So what's the pricing model for your product?
So it's basically it's a per shard, per database. By the list price for the complete configuration, this price can go up to $5,000 a server, which is better. We can, as I said, we have all kind of pricing models for different architectures are different. Yeah.
It's $5,000 per database instance per year.
Which is right.
So like you have 10 shards, it's $50,000 those per year. And you know, if you're replicating or discounting that, those instances are 75%.
Next question, in the back.
Yeah, how do you handle global MVC, C consistency? Like if you're doing your main controller decides to do a read, it has to go to multiple nodes. Meanwhile, another transaction is in the process of committing. It committed on one node but not the other. Do you read back potentially inconsistent data?
You said MCC, so you are inside the business. It's good. So basically, it's when we start a read, so it goes to two places. First of all, we do some sort of two-phase commit. We can have full-blown two-phase commit with XA transactions and so on, and we have some our version of two-phase commit, which is a trade-off between performance and good enough, and very good consistency and transaction performance. And it basically goes like this: if a read, a distributed read, started on all servers, then it's any further transaction that every server does its own MVCC, multi-version, concurrency, and so on. And we get a snapshot of the data as it was when we began to run, like it was in any other database, isolated from all other sessions. It's true that when you choose to go to read replica, then in this case, each query, again, my query number 1 can go to read replica A, query number 2 can go to read replica B, and so on. And then you get different isolation levels, because different servers, again, you can choose if you want to do it, then you are tolerant enough to have it in your application. Okay, so this is answers. Yes.
Just you talked about the solo client, but what's the largest kind of scale? How many servers are you managing at any one time on this, and how many transactions a minute are you doing? Because I saw your benchmarks, but I'm curious what kind of scale.
My benchmarks are 14 servers, and there was 4 Scalebase machines that were handling 14 servers. It's very much dependent on transaction. TPCC transaction is one type of transaction. By the way, TPCC there are 6 types, or kind of some are shorter, some are longer. So it very much depends. We find it very easy. We take much less resources than the database itself. So the number of databases can be 10 or something. We have customers with 10 databases with one Scalebase at front, because the transactions are very small. It's you can, again, the Scalebase balancer can also grow, and you can put more and more as you need. We, as a rule of thumb, we advise whenever you have 1,000 transactions per second, this is the limit for one database, whatever its size may be. Because it's too much for one database. If you have 4,000, let's say, go with 4 databases, and Scalebase can pull out, Scalebase balancer can pull out, most of the time it's 10,000 transactions per second. So it's 1 to 10. And again, it's totally elastic. The database is elastic, and the Scalebase layer is also elastic.
So in other words, basically one Scalebase instance can handle 10.
Yeah.
key limitations for your product?
Yeah, it's basically every MySQL database can be scaled out with Scalebase. We have customers using 4 and 8. We have customers that are using 18 shards. This is in a very unique configuration, with one master, one database outside the array, and 8 databases that use shard tables, with another 8 using for ellipticals and standbys. Everything you can imagine. We have customers that are checking us right now. They want to start with 20 databases, go all the way to 500, because in gaming companies, especially in online gaming, elasticity is of the essence, and they don't want to pay. Remember the graph we saw the first slide, I think? No, you want to be exactly like your demand is. And we had Christmas and the holidays, and we'll have Super Bowl next weekend. And this kind of events, we want to grow to have this load, to handle this load, and then go back to a very a very small footprint to pay less money to cloud and so on. So this is also something that we give very, very easily. We have customers with 70 gigs going to 100 gigs, and we have customers with terabytes. So it's all it's a very wide spectrum in this.
Now to get into like a feature function discussion, but there's this capability we have where you can use or take advantage of the elasticity of the public cloud, where you can auto shard, where you can increase the number of shards and then go back down without going offline. So that capability exists today. And so from a pricing perspective, we don't want to prohibit or constrain that kind of flexibility based on a pricing model. We haven't been asked, but we're hypothesizing that we do some sort of prorated sort of pricing. I don't think on a daily basis or a minute basis or anything like that, but probably on a monthly basis. We can look at how many shards we have on an average, and look at our average, our yearly pricing, come up with something that's fair. That's basically what we do.
I'm more interested in terms of technical limitations, because for my shops, I have like 20 terabytes database with 2 billion connections per day. The peak can handle like a couple million per minute. So those kind of things, it's really impossible to use any MySQL structures unless it's really can be sharded.
Totally agree. Sharding is of the essence here, and here we go. And, because otherwise we'll hit limitations. By the way, Oracle database won't help you much better. So much said about DB2. All the very, very expensive commercials. The things that I've described here, the shared disk is Oracle, all over the place, right? Oracle, very expensive, very prestigious solution. They don't give any solution for the growing amount of data and reads and writes.
Last question, evening. Back.
Scalebase help with the schema changes also, or?
Yeah. No, it's a very great that you mentioned, you brought it up, because it's a very painful thing. In DB, every column you add, you copy the table around and so on. It takes forever. Now, no, with Scalebase, if you have, let's say, instead of one database, you have 20. Okay, each database has become, instead of one big table, it is 1/20th of the table. So yes, you'll log in with your MySQL command line, or your MySQL workbench, or PHP myadmin, or your favorite administration tool, you log into Scalebase. You issue the command, it will work the same. You issue the command alter table to Scalebase. Scalebase will be parallel on all databases. It will return successfully until only after all databases have completed. Now they will complete much faster than one big database that has to copy, because it's parallel, it's a different machine, different IOs. It will run a lot faster. So yes, this is another reason to do sharding. It's not partitioning, by the way. We didn't invent it. So partitioning is also, you can eliminate partition. You can erase the partition. You can eliminate the server. You can do all kind of maintenance on partition, on shard basis, much faster and more. No, it's sometimes enabler. We have customers that didn't touch the schema for years because they can't.
I mean, just so you know, what we do is, when folks come to us and ask us to help them with scalability, they're thinking of sharding. The first step in the process is we'll ask for their general schema log, or general transaction log, the schema, and we'll kind of do an offline analysis to just kind of see if we can help them or not, and what degree can we help them, or while we're not spending a lot of time on transparency, to what degree we're transparent, or what nominal changes that we may recommend if the developers are interested in getting to that level. So that's the step that we take. And then if we feel comfortable, and we think we can add value, and we can go in without any onerous, modifications to your code base, and we'll say, okay, then let's go forward and go into production or go into a simulated mode and see how it works. So I mean that's our process.
I want to thank you all for coming. Doron will be around for any further questions one-on-one. Thank you, Doron Levari, CEO of Scalebase.